Good afternoon, morning, and evening, everyone. My name is Aistis, and today I'll cover 3 topics. So COVID-19 dynamics, testing, and mathematics. I'm not going to explain all of it because they're pretty broad topics, but we really wanted to share some of the experiences that we thought are, we learned something new about COVID that's not necessarily widely expressed in the world, and we wanted to share it with you. Again, feel free to contact me asking now or later, that's okay. So let's start with dynamics, okay? So first learning is lockdown that we did in Lithuania suppressed the virus spread. That's unquestionable. So what you see here on this graph is the proportion of positive tests to total PCR tests that we performed. And this was done in the very extensive testing as previous speakers mentioned. So it's not like we were not testing, it's actually we're testing heavily, but we were seeing the decrease of the percentage of tests we perform to be positive from 15 to 1.5% in a month, which corresponded to exactly a period of lockdown. So essentially the country was in full lockdown, hard lockdown for 4 weeks. We waited until the prevalence of corona, the perceived prevalence was very low, and then we pretty much relaxed quarantine, and this is the Google data showing that the biggest problem became national parks because the usage was through the roof compared to baseline, but grocery and recreation also are returning to normal levels. Just that the normal is not necessarily normal, it's the new normal, and this became now the symbol for the past few months of our quarantine relaxation campaign. You see the little mask over there. We think it's pretty important, and for those who, and the reason why it's important for those who do not yet speak Lithuanian, I'll translate, it says protect each other. So even though the masks may be imperfect for protecting you, but we definitely to slow down the virus spread and the average viral loads in the population, and that's very important. I'll talk about the mathematics of it, but average viral load matters a lot, and masks really help for that. So in summary, lockdown worked. Our strategy was lockdown hard, release hard, but make sure when releasing hard you wear a mask. That's the quick summary. Okay, but then there is another statistic that we really want to look at, and everybody wants to look at, is like, okay, you're testing, are you actually testing the right stuff? So you need to compare your current mortality with your past mortality of the similar years. So in Lithuania at the beginning 2020, the total registered deaths in the country was actually lower than the previous 2 years. So essentially we're not missing a lot of corona cases. People are just, being more careful. Other viruses spread less too, not just corona, and people don't get into car accidents and stuff. So, but that's a very important statistic to check. If you look at other countries, like Belgium, UK, whatever, like the countries who have a large prevalence of corona, you will see you might be missing about half of the cases in some instances who are dying at homes. So, but again, in Lithuania, that's pretty normal. But then, even though we have very low overall prevalence, the dynamics of the virus still matter. So in here, the graph I'm looking might look unusual to some of you, unusual to some others, but essentially, instead of looking at cumulatives and averages, this looks at the just daily COVID-19 cases reported under our testing strategy. And in this one, you see 3 waves of decreasing size. So we had wave number 1, then wave number 2, then wave number 3, which is current one is quite small. And you see that within the country, the waves of corona have been driven by primary 2 regions. So one is this light blue, it's Vilnius, that's the capital city, that's essentially the central hub of the country for both tourism and transportation, has the biggest airport. So this makes sense to be one of the highest drivers. And the second one is our port town. Klaipėda is our port. This is where the ferries come in and things like that. So you also have pretty much the rest is minor compared to those 2. And as you see in this graph, currently the second wave is the third wave we currently see just in Vilnius. The first 2 happened everywhere, but the third one is just, we have a one big region, no hotspot remaining. Okay, so why am I showing this? Why am I showing you these 3 waves? Well, because it's not just in Lithuania. In the whole Europe, it's 3 waves too, if you look at data this way. You could argue about the heights, and obviously when you get to bigger volumes of data, these things get smoother, but if you look at every country individually, you would be seeing the very similar dynamics, just a different magnitude. What it means is like the things that we see in Lithuania could be actually pretty relevant to many other countries. Obviously, the European virus growth and waves are not driven by Vilnius or Klaipėda anymore. It's the big drivers, big countries, but the dynamics are similar. Actually, if you want to look at more of this, there's an excellent website, endcoronavirus.org. You can check this type of dynamical analysis of the systems there. But again, the reason I'm showing this, Lithuania is not that different from Europe and actually the rest of the world, though you would find that in some countries of the world and some regions which do not, they're in worse situation where the second and third waves are going up rather than down. So that's again interesting things to look at. Cool. So where are those waves coming from? Okay, so it's very good. Okay, cool. I looked at the waves, but it's interesting to know why they're happening. Is there an actual scientific explanation, not just the fact that we're seeing them? So we're gonna go level down to the district and city level in Lithuania and look at the corona sort of up close through the microscope. And we're gonna look at two regions. One is Vilnius, that's the capital city, and the surrounding region of Vilnius. And the second case, we're going to look at Klaipėda, which is the port town, and the surrounding region of it to analyze are those waves really there, or is just something that, an accident, okay? So I'll explain this graph a little bit. So let's start with Vilnius. So what you see here, again, it's new daily COVID cases. It's a 10-day rolling average, so the graph is a bit smoother. And what the blue line shows, and let me see if I can actually enable the pointer. So the blue line is the Vilnius, that's the center. And this is how COVID cases were diagnosed in Vilnius. So you clearly see there was wave, then there was a slowdown, and then there was another wave. And the red line is the surroundings of Vilnius. That's the county. So the reason I'm trying to show something interesting about geographic separation and why it matters, but what you see here is that for about 4 weeks there was a wave in Vilnius, followed by another 4 weeks where the wave was in the surroundings of Vilnius, and now followed by another 4 weeks where there are waves in both of them, but the bigger one in Vilnius. So it really shows that there is something in the dynamics, intrinsic dynamics of the virus that makes it spread through sort of contact networks and waves. And of course, just showing one case, it's okay, maybe it's a coincidence, but we would see the same in other parts of the country too. For this Klaipėda, the port city, it's way less, it's a smaller city, so data is not as nice. But you could still argue there's pretty clear phases. Phase 1 of 4 weeks, phase 2 of 4 weeks, and then phase 3 of 4 weeks. If you're a mathematician, you would say, well, actually, if we have small data, there are a bunch of mathematical sorcery we can apply to show that actually it is 3 different waves and three big waves in the center, followed by 3 smaller waves in the surroundings. So actually, even if you have small data, if you're a small country, there is certain mathematical techniques you can play with to show by looking at outbreak severity and things that there is actually a very clear geographic and time separation between outbreaks. Okay, so why is this relevant? Well, I'll show you an example how this could practically be used to track corona or try to predict where it's going to be at a very sort of tactical level. It's almost like, I call it like catching a criminal. We're chasing corona, not running after it, but trying to trap it to see where it's going to be next. So here is a map. And on this map over here, we see the capital city, Vilnius, over here. And then we see a Nemenčinė, which is like a suburban town where one of the first outbreaks in Lithuania happened. And then over here, there is a road that connects them. So if I want to show you now the path of corona, how it moved. So the outbreak in Nemenčinė, followed by the outbreak about 2 weeks later in the care home that's en route to Vilnius, followed by an outbreak about 2 weeks later that's very close to Vilnius at the border. Finally, inside the Vilnius, the shopping centers, where some cases were diagnosed where these people go shopping from outside of Vilnius. So you actually, if you have an outbreak, by looking at the data sort of at a very tactical level, you can start thinking about where it's going to run, where, okay, cool, these people infected in the city, what should I lock down? And I think a lot of people are arguing for geographic lockdowns, and what we applied, this ring quarantine and ring lockdown, ring isolation, it's based on sort of the actual data. That's how virus moves. It moves through towns, but it gives us some time before the second outbreak happens. So we talked about geography and the waves. So just quick summary of this dynamical things. I think these are main takeaways. So one is lockdown works. It definitely drastically slows down the COVID spread. the hard release, we're going to see what effect it has, but for now it doesn't seem to have triggered a big outbreak, at least not in Lithuania. The virus spread is not random, especially during lockdown. It spreads through contact networks, and the unit of spread that's practical is contact network, not individual person. Because I will talk later about how fast corona moves, but what you really want to look at is, cool, corona infected this contact network. What is going to be the next infected contact network? Is it the next city? Is it the places where the people from the infected city work? That's where you want to go after, because the city that's infected, you're basically done. You still need to do the work, but that's not going to kill the virus. So again, not random. It spreads through contact networks, and it goes in multiple waves. And we clearly see it geographically. I mean, I showed you data going level down. So I showed the waves in Lithuania curve, and then showed how these waves are composed of waves in different cities. But if you actually look at geographical neighbors, if you look at Latvian curve or Estonian curve, you would basically see they mimic Lithuanian. And similarly, if you look at Iran, Iraq, Azerbaijan, they'll have similar curves. And then the lag between those waves is about 2 to 4 weeks. And it's yet to be explored, but it seems to be related to the average incubation period. And I'll come back to that as well. So, okay, great. I talked about waves, I talked about incubation period, I talked about the fact that it kind of moves. So how do we testing given this reality? How is it different? Well, first rule is like hunt and don't chase COVID. So the comma has to be right there, not after not. And the reason is it's a very fast spreading virus. It's a SARS group virus. You get infected very quickly. If you get in contact with people, it moves very fast, and I'll prove. Tests are inaccurate. Like, we don't have an accurate practical test. PCR, for a person who doesn't have acute symptoms, I mean, it's pretty much a coin flip at best. Like when PCR, I mean, it's 50-50 at best. I have doubts about that too. So, I mean, you don't have an accurate test, so how can you chase? And test results are lagging. I mean, we mentioned 24 hours. You know, me as an analyst, I want it to be 2 hours, but apparently that's not practical given the current reality. But really, when we started, the lag between the swab being taken to a person to us receiving the actual data was up to 5 days. The ferry would arrive, and it would take 3 days for laboratory to test all the people. Given the SARS nature, or like the speed of SARS, this is totally unacceptable. And even with 24 hours and a 5-day lag in PCR itself being responsive, that's like, you know, basically makes it unusable. So we have to think of this more stronger strategies. And to illustrate specific case of what the speed looks like, so in one of the hospitals, we did an experiment. On the 4th of April, we had 3 registered cases of corona. And we decided to see how many cases there actually are. So we tested the whole hospital, the full staff, all the patients, etc. in the hospital over the next 3 to 4 days. And I mean, 10x is probably under approximation. Given all the inaccuracies of PCR, it was a 10x growth. It's actually probably more. So with corona, what you see, what you have is probably 10x plus. You always have to have this in mind. And then, obviously, if you look at the actual curves, it always spreads in these sort of very fast injections of the virus. So when it comes as a jump. When it comes as a jump. So that means you cannot, just through contact tracing, it's very, very difficult to catch. So what do you do? Okay, cool. So you can't, I argued that sort of random testing of symptomless people plus contact tracing isn't, so what's the alternative? Well, what we did is what we call non-random selective testing. So to learn a bit about this, we fully tested several hospital, care homes, and even one town by testing literally 100% of the people using both PCR and serological testing for antibodies. And this is what we found. So on the left, I have a schematic of the hospital, and each of the white squares is a different ward. So what we found in that hospital is whenever we had corona, a single instance of corona inside a single region of the hospital or the ward, pretty much the whole thing had it, both patients and doctors. And it was the same true for others. Schematically, I mean, obviously there are differences, but systemically, this is how you can think about it. But the wards who did not have corona, nobody had it. So it's this sort of all or nothing dynamic is very important. That I'll get to why this matters, but it's very, very important. The other thing that we did with testing the full town that had an outbreak, the Nemenčinė, the suburban town next to Vilnius, and about 3,000 people and we only had 36 PCR positive results. And we had 63 people who actually had some form of antibodies. So if you think about this, such a small prevalence, in the city of an outbreak, like 1.5% prevalence, plus some already had it, so we probably missed a couple of 1 or 2 waves already. So you really have like this very low prevalence and this sort of all or nothing dynamic. And you also have this extremely high speeds. So you need to be very careful with random testing. So what we did instead, remember, 10x, at least 10x. So what we did not random testing. We thought, okay, like, where does virus actually go? We're trying to catch this criminal. And most virus paths, especially in the quarantine, lead through hospitals in the quarantine, because most of the other movement is restricted, but people still go to hospitals when they're ill. Most vulnerable people are either in hospitals or care homes. You can't get to lower levels of immunity if you are on life support. So really, the people who are most exposed and corona is most dangerous are there. So you want to catch virus as soon as possible before it spreads through the whole hospital. And then on the contrary, young population are less vulnerable to suffer symptoms and hospitalization. Long-term effects are unknown, but given the current realities, it seems that people deal with the virus quite well. So given this reality, what we decided, most tests we're going to do in hospitals and care homes. And we kind of leave the general population testing symptomatic cases only. As Minister mentioned, we did try to run some experiments of random testing of asymptomatic cases in general population, and we found 0 cases. So we thought that's not a strategy we want to pursue. Okay, so quick summary of the testing section. So COVID is extremely hard to chase with contact tracing. So you have to get ahead of it. You can't run after it. Proactive testing of asymptomatic cases in potential hotspots proved to be more effective for us. And from the dynamical point of view, virus spreads with infect all or nobody dynamics. That's critical. And it goes through contact networks. It's both good and bad. I mean, the bad side of it, if you get infected, probably your whole family is going to get infected with corona. The good part of it, it probably suffices to test a couple of members from the family to understand whether there is corona or not. And then the fourth final sort of outcome from testing is like random testing is not that useful when deployed in a focused way. So to give a bad example, test 10 random people from the hospital. Very likely you're going to get these 10 random people in the wards that don't have corona. A better example of random testing is select randomly 2 people from each of the 5 wards in the hospital and test them. And this is what Christina talked about, the Vice Minister, when talking about our current strategy where we go broad and we exploit this property of all or nothing dynamic to be able to test more with less tests. Finally, my favorite topic, mathematics of corona. Again, the obvious things everybody knows, so a couple of non-obvious things, okay? So the first thing is models versus theories. There is a big difference. So standard epidemiological models are established by means of accepted truths. What that means is that things that experts have seen in the operational memory, mostly, that's what people think is true, and which gives you 15 years. It doesn't even go back to the SARS pandemic, the operational memory. So we have to have that in mind. So what if we are facing something new and assume truths no longer hold? What then? What happens to our models then? Well, I mean, then we are basically on thin ice, because our models in that case become theories. And that's a very different thing to a model. And, there is a dictionary explanation of the theory, but what really main difference is that theories you want to experimentally break and refine. So essentially, you have to design experiments so you can try to prove that you are wrong yourself. And that's very difficult one to do, but that's important. That's what physicists do all the time, And then what happens with the theory, after you fail enough time to prove you're wrong, it becomes accepted truth. And that's not what you do with the models. With model, you try to validate that it works. But that's not good enough if you're facing something you've not seen before. And that's very, very important. I know I'm getting very theoretical. So what does it mean in practice? Well, I will show you some common standard model assumptions that people make in mathematics, statistics, and data analysis. Number one that gave me basically sleepless nights is that virus spreads over dense random networks with probability to transmit upon contact less than 1, which is just not true for corona when you look experimentally. I mean, the networks are not dense. The contact probability within families or within people you kiss is not less than 1, it's like basically 1. And however, all the exponential statistical models implicitly have these assumptions. But then you need to go down to the actual original mathematics to understand it. But this all is false for corona. That's why none of the standard modeling basically works. Essentially, to give you an example, if corona spread with probability upon contact of 1, and one symptomless person arrived in New York and was kissing a lot, the whole New York would be infected in 5 days. That's the difference between 1 and less than 1. It's crazy, but that's how this mathematics work. And then other assumptions that are less bad, but average incubation is 6 days. That cannot be true, and I will show you why. Immunity forms for majority of the cases. That a lot of models assume too. That's when the curve starts going down. But we don't know. Then there are some which give me less of a headache. But some people assume that exposed people are somehow just a proportion of confirmed cases. That's probably untrue too. If corona spreads through, for example, common bathrooms and door handles. Number of infectious people are proportional to confirmed cases. Is also not. A lot of these things are very, very dangerous. So whenever you see the conclusions of the model or some claims, open assumptions and check against the slide. Probably they're making some of them. Some are good, but you need to be careful. So this is sort of a layman's version of the previous slide, theory versus a model. And then the last part, which is the sort of the most crazy mathematics, but I think it's also important here for corona. I don't know if you've heard of fat tail distributions. Normally I would do a raise of hands, and some people would have heard of them, and then I would ask a question like, do you know what's special about them? And then there will be no raise of hands. Basically this is just a quote I picked randomly from the internet, but essentially it says, on average, you're using the wrong average. Essentially, and the way it works is normally we have something we call fin tail distribution. That's normal distribution. Mean is kind of close to the average because you don't have many tail cases. That's the thing we normally work with, and that mostly works for 99% of the cases. The more interesting one is something called fat tail distribution. That's something where essentially you see some rare events happening in the stock markets. And the main property, and this is schematic, but essentially the mean can be way to the right of your median. That's the most annoying feature of these distributions. To give you an example, and corona has actually a lot of fat tails. It's a very fat-tailed virus, mathematically looking at it. But essentially, give you an example of the flu. So whether you are a child, or you are me, or you are somebody wiser and older than me, and you get infected by flu, you would both have fever. You would both have symptoms. You can have higher fever, lower fever, but the fact that you would have sort of observable symptoms is kind of normal. Most population would have it. However, if you look at corona, that's totally untrue. There's loads of symptomless cases. That's one example of fat tail. If both me and my uncle gets infected by corona, I may not have symptoms and he will have. So that's a difference intuitively. But mathematically it's important. And why it's important? So I'll give you an example with incubation period. Probably everybody read this article, or at least heard of it in the news, where people did an estimation of coronavirus incubation period and concluded that it's 5 days. But then I'm kind of the guy who likes to read the small print. So there are some limitations of this result. So the authors say publicly reported cases may overrepresent severe cases. Yeah, of course they do, because people symptomless, you don't see them, and the incubation period may differ from mild cases. They don't say how it may be different. And then they look at the median incubation period. But if incubation period is fat tail distribution, as I explained elsewhere in the previous slide, then, median is insufficient. You need to look at the average because it could be way off. And when you look at virology and the average viral loads, it's really bad. And then essentially you have persons, and then they claim that the persons potentially exposed to SARS, although longer monitoring periods may be required to justify it in extreme cases. They say longer monitoring in extreme cases. But remember that this could be a fat tail distribution, and this is what people showed in the New England Complex System Institute recently published a paper where they claim that the incubation period is fat tail distribution. I would say it's even fatter, but even in this one, the mean is 1.6 times the median. And then the other thing final thing I wanted to say is what extreme cases means it doesn't say. And the counterintuitive thing here is if you get infected by high viral load of the virus, your incubation period will be short. But if you get infected by a low viral load, or you have mild symptoms, you'll likely have a way longer incubation period. And that's the counterintuitive bit. So essentially, extreme case may not be that you have extremely high symptoms, but extreme case could be you have extremely low symptoms, and hence you can have extremely long incubation period. Again, I'm not going to go into depth of mathematics. I'm just saying we need to be very careful whenever we see fat tail distribution. Sometimes our intuition lies to us, and it's the opposite. So again, authors usually put these caveats in their papers, and they explain exactly what they show, but then the readers have to make sure they read the caveats. So again, this is, from me, a mathematician, just an ask whenever you make a conclusion, read the small print, at least in the case of a life and death. Okay, so I know I talked for a long time, so just super quick summary of my talk. So dynamics of the virus. So the summary is there is multiple waves. The finer grained you look, the more waves there will be. The significant lag could be between regional outbreaks. So 2 to 4 weeks between different cities. That's what we observe, and it seems that's what Europe observes. It spreads in this all or nothing dynamics between contact networks. Use it to your advantage. Accept it as true. And in testing, try to trap the virus. Do not try to go after it. We did it by looking at hospitals, care homes, and we think they matter, but your country can pick your own strategy. And then post-lockdown, at least we're trying to monitor broad contact networks to make sure we catch virus early. And from mathematical side, like, beware of the models. I mean, don't treat them as truth. Experimentally try to break them to check that they work. And, you may find some you break and some actually seem to work for you because nobody knows which is the correct model. And then when you actually do analysis, do correct mathematics. And then, last but one thing, be a little scared of unknown. We're entering this territory where everybody is relaxing quarantine. We don't know what's going to happen. But don't be scared of me. That's my email address and phone number. Please feel free to call me and talk about Corona. I'm very happy to do so. Thank you.